Hello, so today's format is a bit unusual. We're in my office at CIRAD. I wanted to talk a bit about something that's been on my mind for quite a while. I'm really convinced that we need to concentrate carbon in the soil, not just scatter it around. I'll explain why today. This comes from 30 years of work, 25 years in the tropics, 30 years with Lucy and Segai's team designing agroecological systems that allow us to sequester carbon, improve soils, regenerate those soils. So systems we call direct seeding on permanent plant cover. We've worked pretty much all over the world. About 10 years ago, we wrote a manual on direct seeding in Madagascar. So it was done in Madagascar, but all the principles are general and apply to the rest of the planet. It's available on various websites. And what we're presenting here are the results of a trial setup. In fact, it's in various very contrasting environments all over the world where we cover different ecosystems. But this allowed us to identify the major fundamental general principles that are somewhat universal at the core of how soils and plant microorganism systems function. So we were in West Africa, in Asia, in Madagascar, in Brazil and in France. This makes it possible to cover a good range of systems and diversity. So in these environments, we observed carbon sequestration of up to 2.5 tons per hectare per year over periods of 7 to 10 years. And then for some time now, we've been using a very simple model, the Hénin-Dupuy model, which is quite well known and dates back to 1945. It basically explains to us that mineralization and humification influence the dynamics of carbon. So there are two main coefficients, a mineralization coefficient called K2 and a humification coefficient K1. Nature is well designed. Some would even say life is beautiful because mineralization is low when production is low. So when it's dry or cold, we produce little biomass, but we also mineralize little. Conversely, both production and mineralization can be very high when it's warm and humid. So in a tropical climate where it's hot and humid all the time, you can have maximum sequestration in those areas. As I mentioned, we're talking about 2.5 tons of carbon per hectare per year. To achieve that, you need to produce 35 tons of dry matter per hectare per year. So these are extremely productive systems in order to offset the mineralization that occurs. And the more carbon there is in the soil, the higher it is, the more carbon is lost each year. So the more you have to produce, but also the more you can produce. So these are systems that can function well. And the key to sequestering carbon is to maximize production. In fact, leaves are like solar panels that capture energy and fix carbon. So we need to maximize these solar panels, meaning to use all the time and all the available space we have. And that's why we keep permanent plant cover, use crop associations, rotations, and maximize biodiversity. Everything that helps produce the maximum will also help sequester carbon. So this is an example of corn that grows 4 meters tall. This happens in just a few months, in these climates. And then the other key is to work with the humification coefficient. There are differences in humification between leaves, straw, or wood chips, more woody materials that we get from agroforestry. So this will affect the C to N ratios and the lignin content. The main thing is to always have mixtures of these different materials, but the key is really to produce when mineralization is low. So whenever we can access deep water to produce when the surface is dry, when there's little mineralization, when we manage to produce during colder periods, we'll increase our carbon stock. So after that, we can design different types of systems in all sorts of ways. But as we already wrote back in 2009, there's a key point here. You have to concentrate. So why concentrate? Why is it so important to concentrate? Is because there are thresholds to cross in soil restoration and regeneration. And there are very few studies that show us the production or the yield or basically the benefit of applying fertilizer to soils depending on the carbon content. There is one study in particular from Kenya, which is about 10 years old, that actually shows us that in this situation, with less than 3% carbon in the soil, you lose money by applying fertilizer, especially nitrogen fertilizer. So we see that there is a threshold around 3% carbon in these situations. So there's no need to be alarmed. 3% carbon to produce 1 ton of maize. That's because this study was conducted at high altitude. We're in the east, the west of Kenya, so we're between 2,000 and 2,500 meters above sea level. So there's a lot of carbon that changes very little in the soils. Unfortunately, there aren't many studies that look at this in more temperate conditions. So this threshold is something we first need to reach. In fact, below this threshold, we call these soils that no longer respond to fertilizers, and we need to get past this threshold quickly. So if we look at production in relation to the carbon content, we see it's the same. There's an initial threshold around 3% carbon. We can see that production almost doubles when we cross this threshold. Then there's a short period where it drops again. And then when we're there, there's a period when we're on the path to regeneration. And then there's a second threshold that allows us to quickly increase the rate of the production by crossing a threshold around 4.5 to 5% carbon in this situation. Now, what we need to understand is that not all carbon is the same. Here we have a lot of carbon in the soil, which is actually completely stable, inert carbon. It's carbon that contributes little, that provides little nourishment for biological activity. So we need to distinguish between total carbon and the types of carbon accessible to microbes, which will still be the key element for the biological functioning of soils. And then we'll try to understand what's happening using broader, more global models. So if we plot the possible biomass production and then mineralization on a diagram according to the carbon content, for mineralization we'll have a curve that looks roughly like this, and then for production we'll actually have a curve that looks more like this. So of course the vertical and horizontal axes depend on the climate, the soil, the practices, especially temperature and water, right? But let's say these are somewhat flexible scales. But overall, the main idea to remember is that the curves will have these shapes. And more specifically, if we refer back to the study from earlier, we would be looking at a curve like this. So the idea is to say that there is a threshold somewhere, or several thresholds, at a point where the functioning changes completely. So what happens, and at what level are these thresholds? Well, we have first threshold around 2% carbon, which tells us that in terms of erosion, things will change completely. Above 2% carbon, erosion is very limited. Below that, significant erosion processes can occur. Where exactly are these thresholds located? Well, that's something that still needs to be studied. Is it 3%? Does the climax, the best balance, occur at 5 or 6%? We still have a lot of work to do on that. Most likely it needs to be examined based on the clay content. In particular, there are studies that show us that soil structure in particular is closely linked to the clay to organic matter ratio, or organic matter to clay ratio. Basically, with 10% clay, you need at least 1% carbon to have a proper structure. With 20% clay, you need 2% carbon. So basically, 10% clay, 1% carbon, and you can use these ratios. These are rough estimates that already help us better target our thresholds. So what probably happens next? Well, the forms of nutrition are going to shift. There's a threshold around 2% for erosion, but there are higher thresholds where probably the forms of nitrogen that are absorbed will change. So this is still one of the key points in production. So these forms of nitrogen are particularly linked to the redox potential and pH. And what we see is that the oxidized forms are nitrates, the reduced forms are ammonium, and then the organic nitrogen forms that will be important in this context are quite reduced forms of nitrogen. So overall, what probably happens is that on the left side of the diagram, to the left of these thresholds, nitrate nitrogen will be dominant. And then as we approach the thresholds, we move to ammonium and then transition to organic nitrogen forms amino acids, amino sugars, and a whole range of organic nitrogen forms that are of great interest. So if we look at the mineral forms of nitrogen, according to pH and redox potential, we see that in oxidized or alkaline soils, nitrate will be present. In reduced acidic soils, we will tend to find ammonium instead. So the more energy we bring into the soil, the more organic matter there will be, especially organic matter that is accessible to microbes, the more biological activity there will be, and the more we will move toward ammonium forms. Whereas in oxidized soils with little biological activity, nitrogen will be in nitrate forms. Both forms nitrate and ammonium are accessible to plants, so one might think it doesn't matter much. In any case, they will be able to access nitrogen. But in reality, the form of nitrogen absorbed has a very strong impact on plant physiology. What happens is that a plant absorbing nitrate will release OH, ions to balance its charges, while a plant absorbing ammonium will release H plus ions. So this will significantly alter the pH of the rhizosphere, and this can be observed in experiments where dyes are used to measure pH by color. And we see that a plant feeding on nitrate will have roots with a pH around 7.5, whereas a plant feeding on ammonium will have roots, well, in the rhizosphere with pH values below 4.5. So that creates major pH differences-free pH units. And since nitrogen accounts for 80% of the absorbed ions, this will impact the solubility of other nutrients. So the form of nitrogen absorbed will affect the uptake of all other elements. Next, there are a number of issues related to nitrate absorption. The first is that the root becomes negatively charged, and so positive ions will be attracted by an electric force, which means their uptake will tend to be mostly passive, whereas for nitrates, which carry a negative charge, absorption will require energy. This is reflected at the level of root respiration. A plant that absorbs nitrates rather than ammonium will increase its root respiration by 10 to 15%. A significant portion of that is to absorb these nitrates, and part of it is also to directly convert them into ammonium. So the absorption of nitrates increases the soil pH, which will be problematic if the soil is alkaline. And then there is an energy cost to reducing these nitrates to make ammonium in order to produce amino acids. And here again, we see an energy cost that increases by 15% with nitrates. It takes 8 electrons per nitrogen atom to convert nitrates into ammonium. So all of this represents significant energy cost for the plant. And on top of that, water use efficiency with nitrates can be reduced in cases of water stress. We can see a decrease in water use efficiency of up to 50% in the field. So if there is enough water, everything is fine. Nitrates will cause the plant to absorb a lot of water, leading to rapid growth. Cell turgor will increase cell growth. However, if there is water stress, water use efficiency drops sharply. And in addition, plants that are high in nitrates are not good for health. We try to avoid absorbing too many nitrates. On the other hand, absorbing only ammonium also has its drawbacks. The first is that the absorption of ammonium is antagonistic to the absorption of calcium and especially magnesium. So having only ammonium to absorb can lead to calcium and magnesium deficiencies. It will lower the soil pH. So on acidic soil, this will definitely be a disadvantage. In particular, this can increase the solubility of aluminum and create aluminum toxicities. And then a high level of ammonium in plants leads to a number of toxicities. So that's not good for the plant either. It's too reduced for the plant itself. So it's not necessarily good. And then the last drawback is that ammonium is not very mobile in the soil. So the plant will have to increase its root surface area, so volume of soil explored by its roots. So producing roots comes with a high exploration cost, and it's energy cost that needs to be taken into account. Root exploration, as seen in a recent study in particular, well, the more root surface area there is, the more magnesium absorption there is. So, for example, magnesium absorption is correlated with root length. So that's an energy cost to produce these roots. And often plants will outsource exploration to mycorrhizae, which is much less costly for exploring a large volume, since having lots and lots of extremely fine filaments is much more efficient than having large roots. So this applies to phosphorus, nitrogen, water, and quite a few other things. But if we come back to the nitrogen nutrition of plants, well, in both cases, a pH imbalance is created within the plant. The absorption of NH4 plus will lead the plant to release H plus, resulting in the plant becoming more alkaline. And to a lesser extent, the absorption of number 3 will lead to the plant becoming more acidic. And these imbalances within the plant are generally not good for its health. But if we look only at mineral nutrition, all plants will preferentially absorb a mix of nitrate and ammonium precisely to avoid these pH imbalances within the plant. Now, there are variations between species. Species like wheat and corn will prefer to take up more nitrate than ammonium. Species like rice and soybeans take up more ammonium than nitrate. For oats and barley, young plants will take up more ammonium than nitrate. And conversely, at the end of the cycle, they will take up more nitrate than ammonium. Temperature also plays a role. At low temperatures, in fact, below 13 degrees, nitrate uptake is almost zero. So it's mostly ammonium that will be absorbed at that time, if it's available. And ammonium uptake will increase up to a temperature of about 25 degrees for lettuce, whereas nitrate uptake will increase up to 35 degrees. Maximum nitrate uptake will occur at 35 degrees. And this nitrate uptake has an impact on quality. So the more nitrates there are, the more water is absorbed. So that can be an advantage. On the other hand, the more water there is in the plants, the more nitrates there are. There's a correlation between the two. So from a health perspective, that's not necessarily good. And you can see this with endives, for example. If you use 30% nitrates in the solution and 70% ammonium, you get an average fresh head weight of 196 grams with 2.4 grams of nitrates per kilogram of fresh mass. If you reverse these proportions to 70% nitrates and 30% ammonium, well, you gain 18% in weight. But you more than double and a half the nitrate content. So that's something to consider for health. And for amaranth, you end up with an absorption of nitrates rather than ammonium. We lower the level of flavonoids and phenols by 15 to 20%. So all of these are antioxidants that are generally quite useful in nutrition. But overall, what's fundamental is that the studies themselves are biased. The issue is that mineral nutrition is considered to be dominant in plants, whereas we know that nitrogen nutrition through organic nitrogen is something very common and can even be dominant in certain situations. So the problem is that studying organic absorption is much more complicated than mineral absorption, because with mineral absorption there are only two forms, nitrate and ammonium. With organic absorption there are dozens of amino acids and dozens of amino sugars. So to be sure you've covered all possible forms, there are hundreds of parameters to measure. There's a very rapid turnover of certain amino acids in the soil with a half-life that can be measured in days or even hours. So this makes studies much more complicated when trying to account for everything, given how fast the dynamics are. And then in particular, there's competition with microbes for absorption. So will the plants manage to take them up first? What is the concentration in the soil of amino acids and amino sugars that is necessary for this form of nutrition to dominate? These are all questions that remain. What we do know is that there are hotspots of amino acids, particularly in earthworm casts. where it is very likely that the plant will be able to feed on amino acids. In any case, what is certain is that we know plants can absorb amino acids and amino sugars directly without them needing to be mineralized into nitrate or ammonium. And then if it has the choice, actually there are studies that show that if you give the plant only nitrates, it will absorb a lot of them. If you give it only ammonium, it will absorb less because it can cause toxicities. If you give it only amino acids, it will take just what it needs and it will be balanced. On the other hand, if you give it the choice between the three forms, it's the organic forms that the plant will prefer. So there are still quite a few points and questions we need to consider in research. But overall, what apparently happens in soils is that on the left, nitrates are dominant. At the threshold level, it's ammonium that starts to come through. And then on the right side of our diagram, the organic form becomes dominant. So basically, it's nutrition through carbon. For that, there needs to be plenty of carbon in the soil and there need to be microorganisms. This turnover is largely due to microorganisms that produce these amino acids. There also needs to be a microbial community that is fairly balanced, not too reduced, not too oxidized, so a facultative aerobic flora. They need to be mycorrhizae. And at that point, overall, it completely changes how things work. When we are dealing with strictly aerobic forms with dominant nitrate, plants will have a lot of difficulties. They have to compensate for this. They use up a lot of energy, so production will be low. So basically what you need to remember is that to the left of this threshold, it's the soil that feeds the plants. The plants draw from the soil and give very little back to it because carbon production, carbon fixation is limited. To the right, actually, the plants feed the soil more than the other way around. They take nutrients from the soil, but they bring a lot of carbon. They bring life into the soil, which helps solubilize nutrients. So overall, the plants feed the soil more. That's where we can achieve sustainability. The problem is that agronomic models are mostly based on soils with little carbon, because that's what predominates in our agricultural environments. Whereas it would probably be interesting to work on agronomic models in places that are more like forests or grasslands, focusing on how they function. We really need to replicate how forests and grasslands work, meaning having carbon in the soil and biological activity that drives everything. We can also look at soil carbon as a kind of bank account. In fact, to the left of the threshold, we're overdrawn. Every month we pay interest, we have fees, everything costs more, it's hard to produce much, and it's hard to pay back the capital that's overdrawn. And so sometimes it can even be worse than that. But on the right, it's the opposite well-stocked bank account. Every month we receive dividends, we have few fees, we can pay for everything at a lower price, buy in bulk, and overall everything works better. And then on the left, sometimes you can even see it as erosion. It's bailiffs coming by, seizing your means of production. So overall, we're just sinking deeper and deeper. It's one of the rare cases in nature or in physics, in chemistry, where the less you have, the less you get, and the more you have, the more you get. Usually when you have high pressure and low pressure, it balances out. High temperatures and low temperatures, it balances out. High concentrations and low concentrations, it balances out. Here we're in a situation where the more you have, the more you'll be able to get, and the less you have, the less you'll get. Aside from money, I can't think of any other examples. What makes this unique case possible in nature is that we have free energy provided by the sun. And if we have plants, if we have soil that's able to store this energy, we'll be able to produce everything, each time a little more. So there really is a threshold to cross, a tipping point. And agricultural production, like agroforestry production, should essentially take place in environments that are above these carbon thresholds, whereas most agricultural production actually happens below them, often in Africa. And you could say that in Europe we often have an agriculture that's on crutches. where we are forced to compensate with external energy and with subsidies, well, basically, to make up for being exposed. Bioenergy production, livestock production, these are often done in those environments, especially in Africa. The more degraded it gets, the more animals there are to exploit the little fertility that's left. Whereas ideally production would happen here, where we wouldn't be degrading the land. We could export the production surplus compared to mineralization without depleting the soil's fertility. So we really need to get back to doing that, because on the entire left side of the diagram, there is no sustainable production. You can be in an organic system, if you don't bring anything back, if you leave the land bare, you won't achieve sustainability and you won't be able to regenerate the soil. Sustainable production goes hand in hand with high yields. That's something that really needs to be said. To be sustainable, you have to produce a lot and leave a lot on the soil to feed the soil as much as to feed people and animals. And quality isn't linked to low yields either. To produce quality with rich elements, those elements need to be nourished primarily by biological activity, by balanced products in a healthy environment. And that can only be achieved with high yields. So we need to be able to move quickly, to restore things quickly. And the more degraded it is, the harder it gets. In fact, the more difficult it will be to recover, because with every interest payment every month, we pay a lot of interest. So we can no longer pay back the principal at all. So any systems that don't allow for carbon to be replenished or only provide a small amount of carbon will keep us stuck in the difficult zone for a long time, making the transition very complicated. Especially since we've seen that there's a tough phase here, which is probably due to the shift from an all nitrate nutrition to an all ammonium nutrition after passing through an intermediate stage. And so for as long as we remain in this difficult zone, the transition will be truly complicated and could quickly become discouraging. So we need to aim for a rapid transition. And to make a rapid transition, we need to bring those carbon levels back up as quickly as possible. And for that, we need to focus. If we don't have enough to cover the entire area, we'll concentrate at the plot level, at the farm level, or at the territory level. But overall, if we just sprinkle a little everywhere, we stay on the left side of the diagram and we can't make any progress. That's what the Burkinabe farmers understood, those working on completely degraded soils, who dig half moons to collect all the water that falls and put in all the manure they can get. They put in the cow manure they have all the organic matter they can gather within a 10 centimeter diameter. They plant a cornstalk, a bean plant, but right there, locally, they've moved back up to the right side of the diagram. They can produce and then gradually expand. But if they were to sprinkle the little organic matter they have, given the level of soil degradation, they would achieve nothing. They clearly understood that by concentrating, they could make progress. So the idea is to make gradual gains. If we can't manage to provide enough biomass, well, in market gardening, that's something we can do fairly easily. Large additions of ramial chipped wood, biomass, or straw will allow us to quickly move past the threshold to the right and then make progress. On the other hand, when we don't have those options, concentrating on the rows or on certain parts of the plot will probably be more effective. And then what we need to remember is that every time we till the soil, we remove plants that produce carbon, fix carbon, and generate biomass, and we encourage oxidation by the sun's UV rays. So we lose ground, we go a bit backwards every time we plow. So soil tillage has several negative effects. So now the big research questions are, where exactly are these thresholds? What exactly is happening? And we're going to have to get to work on it. And that's it. I'd like to thank everyone again, from Lucien to François, and say see you next time.